Hello everyone, welcome to 𝐿ustraca. So in this lecture, I am going to discuss about the plate forces in STAAD Pro. In the previous lecture, I have explained how you can get the in-plane forces of a plate element, or you can say when you will be designing the shear wall, how you will be getting the in-plane moment and forces to design that shear wall, right? Now, in this lecture, I'm going to talk about the out of plane moment and shear. So whenever we are going to design, suppose a you can say retaining wall, or maybe a simple slab which is undergoing the bending, or maybe a tank wall. So in these cases, this out of plane bending moments and shear force is very important for us. Many of us, you can say, often get doubt that how to interpret the result that STAAD is giving in terms of the plate results. Okay, so plate moments and forces. So in this lecture, I'm going to you can say elaborate that in detail. So let's get started. Here I have created three plates. You can see two vertical plates and one horizontal plates, and I have meshed it actually. Okay, these are the very basics. All of you know how to create a plate and how to mesh it actually. So I have just create a simple plate of a certain size and I have meshed it. And if you see here in the property, I have given a 200 mm thickness to this. I can say plates also. So if I show you in the 3D view, you can visualize it. So these are the three plates, two vertical and one horizontal, right? So we all know that whenever we are applying some load on this plates and we are going to see the forces on these plates, so the forces, moments, everything is depending on the or you can say sign convention, or the naming of that forces, all everything is depending on the local axis of the element. So it can be a small beam, it can be a plate, it can be a column. So everything, whatever forces we will be getting in terms of the local axis. Okay, so first of all, we have to understand the local axis orientation of the element. Okay, so what I will do, I will go back to the geometry, and here first of all, let me turn on the local axis of these plate elements. So I will just press Shift T to turn on the local axis of the plate elements. So you can see here we have three axes, as we have the global axis also. Here also local axis, three local axis. X, Y are the plane axis. You can see here in case of this vertical element, X and Y is the vertical plane, and the perpendicular to that plane we have the Z axis. Correct. Similarly, here we have X and Y, and perpendicular to that we have the Z axis. Okay. Now let us take just one element from here, one element from here, and one element from here. Okay, so I'll just click on this one so that I can easily explain these things. So if I just focus on this particular thing, okay, let me discuss in one plate, and we will be later on we'll be understanding the other plates also. So if you see here X and Y we have in this way. So this is my Y, this is my X, and the vertical plane we have the Z axis, and this is my local axis of this plate, local axis of the plate element. Now this orientation of X and Y, obviously these two will be always in the plane. If you are drawing the vertical element, it will be a vertical plane. If you are drawing a horizontal element, it will be the horizontal plane. But the direction of X, whether the X will be in this side or that side, whether the Y will be upwards or downwards, that will be depending on from which direction you have started creating the plate. Suppose I have clicked here first, then here, then here, then here. Then the orientation you will be getting, it will be different if you start from this point or if you start from that point. Correct? So based on that, this plate orientation actually I can say being generated. Now the main thing that we have to understand, that instead, suppose this is my plate and let me draw the elements. Suppose this is my y-axis, this is my x-axis, and this is my z-axis. So whenever you will be seeing moments, remember, whenever you will be seeing moments, if I just draw the thickness also of this plate. Okay, so moments always along the direction of the axis. Suppose I want to see moment mx, the result STAAD is giving, suppose mx. Okay, so mx will be always along the direction of the you can say axis. So my x-axis is this one, along left to right. Okay, correct. So the moment will be along this direction. Now how the moment will be, whether the moment the plate will, suppose this is my plate, now whether this plate will be bending like this or bending like this, which face will be under hogging, which face will be under sagging. So that will be based on your loading, right? If the load is from top, then the plate will bend like this. If the load is from bottom, the plate will bend in the opposite direction, like this, right? So we cannot define, or we can say we cannot say that which direction the plate is going to bend. But what is more important for us, that suppose STAAD is giving mx and my. So in this case, how to understand, suppose STAAD is given some you can say -5 and my is suppose 5. Okay, now how to understand, or another value STAAD is given 5 and here suppose -10. Now in this case, how to understand whether the negative value is you can say hogging, or the positive value is hogging, or the negative value is sagging? How to understand that? So always remember, the direction of the z local axis, direction of this z local axis will be always positive. Along the direction of the z local axis will be always positive. Positive when this face is under tension. Okay, if z is upward, then if the upward face is in tension, then it will be positive. So that means the moment like this, the moment when the plate will be bending like this, okay, that means the plate is bending like this, then the top face will be positive because it is under tension, and the bottom will be negative and it is under compression. Where it is true? It is true when the z is up. Okay, it is true when z up, z local axis is upwards. Okay, similarly, if I draw another plate, suppose let me draw it here itself. Okay, now in this case, suppose and I have the z-axis downwards. Okay, I have the z-axis downwards. In this case, what will happen? In this case, it will be totally opposite. That the moment, suppose I am talking about mx only. This is the mx moment, actually, mx moment. Here also I am showing the mx moment. The my will be the same direction. Okay, so the bottom face, if I draw it like this, okay, so now if the bending direction is like this, then in this case what will happen? The plus when tension and minus when compression. Now we have, suppose we have load which is making the plate bend in the downward direction. So suppose the plate is bending like this. That means the moment is in the same way, same direction, so it is correct. the bottom is under tension, so it will be positive, and top is under compression, so it will be negative. Now if the load is acting from the downward direction, so in this case, if the load is acting from the downward direction, so in this case the plate will be bending like this, right, when load is acting from downward direction. So in this case what will happen? In this case my top face is under tension, so negative will be tension and it is my top face, right, and positive will be compression, which is our bottom face. So I hope you understood. That means the in whichever direction the Z is there, in that direction the sign convention will be always positive. Now if the top, suppose Z is up, then top face, if it is under tension, tension will be positive. If it is under compression, compression will be positive, right? If Z is downwards, then bottom face, if the bottom face is under tension, tension will be positive. If the bottom face is under compression, compression will be positive. So whichever, tension or compression, whichever it is, that will be positive value when depending on the direction of the Z. Okay, so now if I just you can see here, so that means if the plate bends like this, suppose if the plate bends like this, and if I say this is my, suppose, external face, and this is suppose my internal face, okay, and the plate is bending like this, so that means this face is under tension and this face is under compression. Now can you tell me what is the sign convention for this? What is the sign convention? As the Z is outward direction, so the tension will be positive and the compression will be negative. Okay, because this is the inner face, so the inner face will be under compression, it is going to be the negative because Z is outward, so the outer face will be under positive value. Now if it is under tension, so it will be, tension will be positive, correct? Now if I make you understand the other way, suppose the similar thing, now the plate is bending in this direction, the plate is bending in this direction, this way, then what is happening? So that means here the inner face, so this is my in, this is my out, my inner face is under tension and my outer face is under compression. Okay, so if I ask you to define the sign convention will never change, Z is outward, so outward this compression will be positive and inward the tension will be negative. Okay, now if I just turn on the whole object, and you see here we have the two plates where Z in both cases, suppose this is my internal and this is my out, this is out. Okay, so for this plate Z is outwards, for this plate Z is inward, correct? Now if I want to see the moment, suppose I have applied some load on it. If you see here, I have applied some uniform lateral load on the wall. Okay, now what I will do, I will just analyze it once. No print, add, let me run the analysis, run analysis. Okay, post processing mode, done. I will go for the plate stresses and suppose I will see the moment mx. Fine. Now what do you understand from this moment mx? Okay, this is what we need to understand now. What do you understand from moment mx? Here you can see in the shear membrane bending, or if you see, this is the stress summary actually about the maximum. Okay, so if I just show you from the stress summary only, suppose I want to see the mx. So what you understand from this mx? What you understand from this mx? What I will do, let me just do one thing. Let me create some group. For this, Control G. Suppose I will make plate. Suppose it is wall 1. I'll click on OK. Associate. Okay. Then I will create another one. Wall 2. I will go to plate. Okay. I'll select this. Associate. And I will see this as suppose slab. I will go to plate. Okay. Associate. Okay. Now I will run the analysis again. Okay, post processing. Fine. Suppose I want to see only this for this plate. Okay, for this wall. So I'll select this wall. I will make it view only this, so that we can easily understand. Okay. Now I will go to here in the plate stress. So results, plate stress, and suppose I want to see the moment mx. Any moment you click, then we will understand one. So now what you are understanding now, if you see here, this in the stress summary, if I just right click, result setup, load this load and range, suppose the group wall 1. I want to see the results only for wall 1. Here when we see the stress summary, it is giving summary for all the elements present in the you can say this particular view. Okay, so whatever is maximum value for all the elements, it is giving initially. So you just have to group the elements for which you want to see the result, and then you can click on OK. So now we are seeing result only for this wall 1. So what does this mx? You can see mx, two values are maximum. One is 1.404, another one is 0.106. One is positive value, another one is negative value. So what do you understand from this? See, now what we expect, that we applied load from this direction. We expect that the wall will be bending like this, right? Wall will be bending like this. So the outer face will be under tension, and the inner face will be under compression. Okay, and obviously as it is a cantilever wall, so the tension value will be higher. Correct? Tension value will be higher in the outer face, right? So as that is this direction, so we expect that the tension value, that means the hogging moment, tension means this is the hogging moment, right? And here we have here actually we cannot say hogging and sagging. It just, if you see here, it will be something like this, right? Yeah, so the hogging moment will be positive and the sagging moment will be negative. Okay, so this is, I can say hogging. In plate, okay, let us not get into this confusion now. Let us understand by tension and compression only. So the outer face is under tension, and we expect that the moment in the outer face will be getting positive. Okay, so obviously as it is a cantilever wall, in these plates we expect that the moment will be higher. And which moment will be higher? As it is a cantilever wall, other than the horizontal moment, which is along x direction. If you see, horizontal moment means along x direction, that means the wall will be bending like this, as it is a cantilever wall. So we expect that wall will, this particular bending will not be you can say more, but this bending, okay, the bending along y direction, okay, like this, in this wall like this bending will be higher. Okay, and we expect that this outer face moment value will be positive value. So if you see here that the mx moments, which is the horizontal bending moment, it is just 1.40 1.404. Okay, and this is also at the bottom. And if you see here where we will be getting the sagging, obviously at the top area, because the top is going this direction. So if you see here, if I click on this negative moment, which is the compression phase, right? That means the inner phase. So that is in the negative value. And we expect that the moment along y, this moment, okay, the vertical direction moment will be higher, and in the bottom location it will be under higher tension in the outer face. So if you see here, this 8.334 my, 8.344 my, it is the moment that we are getting at this bottom face, bottom. Now how you need to understand, you will be understanding whether it is in the outer face or inner face. Obviously it is a cantilever wall and the outer face will be under high tension. So this positive moment, and we also see that z is outward direction, so obviously this positive moment will be for the outer face of the wall, and the negative value we don't get here in my direction. There is no negative value. Okay, mostly the positive value only. So what you can do, you can provide minimum reinforcement in the other face, and there is no compression value, right? Correct. Actually this is what the, I can say, behavior should be, because there is no prop. What I draw in the bending moment diagram, it will not be like this. I have drawn the bending moment diagram like this. It will not be like this. It will happen when we have a prop here. Actually we don't have anything here, so it's like this fixed. So the bending moment will be like this only. Okay, so the outer face will undergo tension like this. Correct. So now, so what you understood, that this 8.344, it is my outer face moment. Okay, this is my outer face moment, and as this is cantilever wall, and so this bending along y direction, this local axis y direction, will be my major bending. So you can see here, obviously by seeing the value also you can understand that this is my major bending. Okay, in mx, when the wall is bending like this, suppose like this, it should bend like this only, sorry. Okay, so here positive value we are getting 1.404. It should not be bending like this, basically, because we have not applied any you can say support in this side faces. Okay, so horizontal direction, if you see here what it says, 1.404. so this is also the outer face. This moment is for the outer face and this moment is for the inner face. Okay, the negative value, the negative moment is for the inner face. Now how it is bending, that you need to see from the deflected shape. You can see here, and then you can decide whether this is for tension or compression. Okay, hogging or sagging, that you can define from the deflection diagram. So if I just go to, sorry, displacement, let me just clear this. Let me increase the deflected shape. You can see this is the deflected shape. There is hardly any bending along the x direction. Actually, if I see this other face, hardly any bending along the x direction. Okay, the most of the bending is happening along y direction, and you can see here actually there are some bending happening in this way, like this. So that means in horizontal direction, this face moment will be 1.404, and this is positive, and this face moment, it is something, the very minimum value, which is negative. but this is in tension actually, and this is under compression, you can say, in case of the horizontal case. Okay, now the same thing I can explain if I assign it. Let me just go back to the analytical model view, display a whole structure. Suppose I will assign support to these faces also, then in that case you will see the horizontal moment also. So especially when you are designing tank walls, in this case you will find the three sides are supported by the other side walls. Okay, so in this case the horizontal moment will also be very you can say dominating. So I will just assign a support and I will run the analysis. Okay, now I will go to post processing mode. Done. Okay, now what I will do, I will go to plate, anything I will take, suppose mx, and what I will do, this diagram is not important, these values from the stress summary, it is main important thing which you will be using for design actually. The result I will take wall 2. Okay, so the results are for this wall. I will select only this wall, view, selected objects only. Okay, so now here in this case my load is applied from this direction. Okay, my load is applied from this direction, correct? So what we expect that the wall should bend like this. No, the bottom part will not be bending that much. The bottom part will not be, the top and the mid portion will be bending. The bottom part is supported like this. Okay, so in this case the horizontal movement will be more governing than the vertical movement. So that means the mx values will be more governing. Okay, so here at the edges the movement is like this, I should say like this, and at the you can say mid part the movement is like this, correct? So here we will get, what should I say, hogging, and that will be in my inner face, or say this side is outer face, suppose outer face, and this side is inner face, hogging, and here it will be sagging, that is in the inner face. Now in my case, in this case, this sagging value, or I should say this you can say inner face bending, will be positive value because this face is in tension, and here also it is under tension at the edges, and it will be under negative value. And in this portion, the moment which is compression, actually I'm not saying moment, suppose the compression, and the moment value will be negative because this is the tension is in the opposite face of the direction of z. This is my z, opposite face we are having tension, so this face will be negative, this face will be positive, sorry, this face will be positive, this face will be negative. So the compression value that we will be getting, it will be positive, the tension value that we will be getting will be negative. Okay, so let us see the values, then we will understand. So what we expect that the mx moment will be higher moment, and that too the positive mx moment, which is this, it will be in the center, and the negative mx moment will be at the edges. Okay, why negative? Because tension in the opposite direction of the z local axis, okay, in the edges, and in the center tension in the along the direction of the local axis z, so that means the mid face. Okay, so in this case this tension will be positive tension, correct? So if I see the mx, first you see the values. As we expect, the mx moment, the horizontal moment, is higher moment. Obviously one is positive, one is negative, and if you see, the vertical moment is very less compared to the horizontal moment. Now, as I said, the positive value will be in the center. Okay, because the bending at the center is happening along the direction of the local Z, and the bending at the edges is happening opposite to the direction of the local X. Here it is tension. Here also it is tension at the edges. This tension is negative, this tension is positive. Okay, this tension is positive, this tension is negative. So if I click on the positive value of the tension 0.793, sorry, I will select this load. So it is happening, you can see at the top. So if I just, yeah, so it is happening at the very top, the maximum value. So if I draw a diagram like this, okay, and you can see this positive value, as we say, the positive value will be at the mid part. So this plate is also at the mid part, and here we are getting the maximum moment value. And then in this case, this positive value will be in which direction? Outer face, sorry, this is my inner face, this is my outer face. Now tell me that this positive moment 0.792, it will be for the inner face reinforcement or outer face reinforcement. With this moment, what you will be finding? Inner face reinforcement or outer face reinforcement? Obviously, as the bending at this mid location is happening along the local Z axis, which is inwards, so this moment is for inner side, right? Similarly, the negative moment, if you see, minus 0.831. So if I select this, it should happen at the edges. So I just select this, and you can see it is happening at the edge. Okay, so for this moment will be at the outer face. So for this moment is happening here, and this bending is happening at the outer direction. So for this moment, we will be providing the outer reinforcement. So here it is minus 0.831, and here it is 0.791. I hope it is clear to all of you. Okay, how to see the moments? Fine. If bending is happening along the direction of the Z, then the tension in that direction, in that face, will be positive. If the bending is happening opposite direction, the tension at the other face will be negative. So it is all about this Z direction. Z is this direction. Any value, tension or compression will be positive. So by seeing this only, you can understand how you need to interpret the result. Okay, now let us go to the slab part. Okay, so I will just clear all this. I'll go to view, display structure. I will select only this slab. Okay, now you have to tell me what will be the answer for this. So here you can see that Z is up, Y is along this direction, X is along this direction. I will also come to the reinforcement part actually. So Z is up, Y is along this direction, X is along this direction. Correct? Now if I go to the analysis post-processing, and if I first see the deflection diagram, so you can see here, this is how the deflection is happening in this case. Okay, so that means we expect in this, by seeing this bending direction, we expect that the major bending moment we will get along the y-axis, right? Major bending moment we will get along the y-axis, and a very high little amount of bending is happening along the x-axis also. So the minor bending moment will happen along the x-axis. Okay, this is first interpretation by seeing the this result. Secondly, the higher bending moment, obviously it will happen at the center of the slab. somewhere here. Okay, center of the slab or center strip of the slab. So as the z direction is upwards, okay, as the z direction is upwards, so in this case the sagging moment which is dominating, in this case which is dominating, it will be, or I should say, tension at bottom. So what will the sign convention for this? As z is up, okay, so opposite direction we have tension. Okay, so this is plus and this will be minus. So here the tension bottom face we will be getting negative moment, and for the top face we will be getting positive moment. Okay, and for the negative moment value it will be higher value as the sagging is dominating here. Okay, and again what another interpretation is that my, that to the negative my will be the dominating, and also the negative mx will be dominating. If you see the bending like this, okay, so negative mx will be dominating. Fine, first this, second this. Okay, so that means this is negative means my bottom face, negative means my bottom face moment, and for this moment we will be calculating the bottom reinforcement, not the top reinforcement. For top reinforcement we will find plus my and plus mx. For plus negative my we will provide bottom reinforcement along this direction, along the y direction, and for negative mx we will provide reinforcement along this direction, that too in the bottom. For positive my we will provide top reinforcement at the along this direction, and for positive mx we will be providing reinforcement at the top along this direction. Okay, clear? Okay, fine. Now I will go to the plate results. I will go to plate stress. I will take any mx or my, whatever it is. My main value we will see from the stress summary. For now I will right click, go to result setup. Already the load is selected. I will select this slab, so I'll get results for only slab. Okay, so don't see these contours, just see these values in the stress summary. So what we expect that negative my value will be higher, and that will be my bottom bending moment, when sagging moment. Okay, so if I see my, and if you see the negative value of my minus 5.962, okay, minus 5.962, this is my negative bending moment. And if you see, compare with mx or my, even the positive value, this is the higher value. So this is correct, our interpretation is correct. So for this moment negative minus 5.962, we will be providing bottom reinforcement for this, or this is my, you can say, bottom moment along y direction. Okay, so this reinforcement, I will just draw the reinforcement. It will be provided for my equal to minus 5.962. okay, fine. So this is my bottom. Now what will be the top moment along this direction? So it is clearly seen that the top moment, I will see top moment along this direction. So the top moment is 4.001. Top also very high only, as this direction only spanning higher. So this is my top moment. Okay, for this top reinforcement we will be calculating. Okay, so what is the top moment for which we will providing? My equal to 4.001 kilonewton meter. Kilonewton meter per meter means for 1 meter span it is giving actually. Okay, this is not an issue. So just kilonewton meter you can write. For this you will be finding the reinforcement. Fine. Now let's talk about mx. In mx also we expect that the bottom moment will be higher. So that means the negative, I will draw this value to here. So the negative mx value will be my higher value, and it will be for bottom moment. So you can see here the negative moment, which is minus 2.887, it is my, this is my bottom moment along x direction. So for along this direction we will be providing reinforcement. This is my bottom and this is for minus 2.887. and if I draw the top reinforcement, this is my top reinforcement. Okay, this is my top, and what is the value for this? Mx equal to, you can see here, 2.233. So 2.233. Fine. I hope it is clear now how we will be providing now for plate or slab or wall, whatever it is. Why? Because Z is up here. Z is, this is Z. Z is this direction. Okay. If you see My, you will provide reinforcement along Y direction for this moment. If you see Mx, you will provide reinforcement corresponding to the Mx moment along the X direction. Okay. In plates, moments are along the direction. In beams or columns, moments are about the axis. Okay. So Z is up, so all the plus values are at top and all the minus values are at the bottom. Okay, fine, clear. Now it doesn't matter, it is tension, compression, hogging, sagging. You just have to do this thing. You have to see by you can see in the displaced shape or deflected shape which corner you are getting tension, which corner you are getting compression. Okay, or you can say which corner you are getting sagging or which corner you are getting hogging. Okay, based on that you need to interpret this result. But the sign convention, I hope it is clear to all of you now. So we talked about the moment. Now let us talk about a brief about the you can say shear. Okay, now this, in this shear, STAAD is not giving the shear force, but STAAD is giving the shear stress. Okay, STAAD is giving the shear stress. Now if you see one thing, actually the shear stress is very less here. Almost zero here actually. Okay, shear stress is almost zero here. Okay, fine. So now let us understand the shear part. Let me go to the any wall, then that will be better, I guess. So here let me show here itself. This is my plate. Okay, this is my axis, X, Y. Suppose Z is up. Now I have nothing to do with Z and all. First of all, because shear, negative or positive, whatever it is, the value is more important. The absolute value is more important. In shear, we do not have hogging shear, sagging shear, right? It is just the, and I am talking about out of plane shear. Remember, the bending also out of plane bending means it is not in the same plane. It is the out of the plane like this. And shear also I am talking about the out of plane shear like this. Okay, which is along the thickness of the member. Correct. Now if I see the shear stress in STAAD, basically these two things, SQX and SQY, are giving me the shear stress. Okay, now how to understand which is the SQX, which is the SQY? See, this is my local axis X. Okay, this is my local axis X. So the phase perpendicular to this local axis, this phase, suppose I have not this phase, let us cut any phase somewhere here. Okay, let us cut any phase somewhere here. So if I see this phase, we will be having some shear force like this, right? Acting like this or acting the other direction, whatever it is, along the direction of the force. Okay, so this, in this phase, whatever is the shear stress that we are getting, shear stress means shear force VU divided by B into D. Okay, so D we have, this is my D. B also we have, B per meter or something. Okay, so on this face, along this face, whatever shear stress is acting, this shear stress will be my SQX. Okay, so the face which is perpendicular to the axis, if it is along x-axis, perpendicular to the x-axis, so the shear stress along this face will be my you can say SQX, and the shear stress, if I now draw a different drawing, suppose like this is my, again the same X, this is my Y. Okay, so the shear stress, suppose along, I have cut one plane here, so the shear stress along this face, what we will say this, we will call it as SQY. SQY, fine, correct. So now if you see, we have some values for SQX and SQY. See here, so the maximum shear stress, for this plate, if I see the maximum shear stress, SQX means this. Okay, SQX means, if I just turn off this plate view, none, I will make it none, I do not need it actually. Okay, so SQX means see along this direction, so at any point along this plane, this is my SQX. I am getting it in this plane, in this plate. If you see in this plate, so at the center of the plate along this direction, in this face, this is my SQX equal to 110. At this point I am getting the maximum shear along the Y direction, which is perpendicular to the X direction, so that's why it is XQX. Okay, perpendicular to the X direction, face perpendicular to the direction. Okay, now if I see the SQY, maximum we are getting 144 in the same plate, but the plane direction will be changed. Now the plane direction I will cut at the center of this plate, and it will be something like this, and it will be my SQY equal to 144. Okay, so for this shear you will be finding VU by BD, you will find the shear stress. So this is the shear stress it is giving. But here one thing you remember, STAAD is giving shear stress based on the total depth of the section. Okay, so you need to convert it to the, for the you can say whatever depth you are designing, so you need to convert this value somehow. Maybe you will find, because ultimately you need the VU, right? Ultimately you need the VU, or if you see this is my tau V, then you will find what is the tau C or tau C max, right? So that you can do in the design, but this is how you will be interpreting the analysis result for the plates in STAAD, especially for out of plane bending and out of plane shear. For in plane bending and shear, I have already explained in the previous lecture that available in my YouTube channel. Clear, all of you? Okay, so if you still get any doubt, please do watch the lecture a few more times. Okay, then it will be clear to you. You try to you can say create one you can say case for yourself also, and where you have applied some load, and you know in which direction you will be getting the bending, and you know in which phase you will be getting the higher moment. Okay, and then you check the results and you try to interpret these results. Okay, then you will be getting better understanding about this you can say sign convention of in STAAD. Okay, so if you have any suggestion or if you have any doubts still, you can always write me in the comment. I will try to solve your suggestions or comments, and sorry, I will try to solve your doubts, and if you have any suggestions, write me in the comment box. I will try to create some lectures on based on your suggestions also. Thank you, and see you in the next lecture.